This is a Calculus 2 class. We're gonna study comparison test. Last week, we learned how to use divergent test, integral test. Today, we will learn how to determine whether impingement series converge, diverge using two powerful tools, the direct comparison and limit comparison. Both tests rely on the idea that if you can compare a complicated series with a simpler one whose behavior we already know, like geometric series or piece series, we can infer convergence and divergence based on the comparison. We can justify a comparison by verifying condition for positivity and proper inequality relationship. Let's get started comparison test. Let's have an example before we introduce comparison test. Look at this series, guys. Looks familiar? This one looks similar to this series. Can you figure out what kind of series it is? I expand sigma 1.5 plus 1 over 2 square plus 1 over 2 cube plus 1 over 2 fourth power. This is geometric series. Ratio gonna be 1.5, which means this series gonna be converged because ratio gonna be between -1 and 1. What is gonna say series of left side? I guess this left series right here, guys, this series also might converge because there is not huge difference to the geometric series. So our guess is this is converge. Why? We're gonna discuss why. Look at another series. This looks like a piece series, but not exactly piece series, but looks familiar. So I have this piece series. Only difference is denominator. Here is n, here is n plus 1. But we know that this piece series gonna be diverse because p equal 1. That's the harmonic series. So we know that this is diverse. So you're gonna say this series gonna be also diverse. I think your guess is right. Let's talk about direct comparison test. First, we have a sequence of AN, sequence of BN. Sequence BN, each term of Bn is greater than each term of An, which meaning is A1 less than B1, A2 less than B2, A3 less than B3, something like that. So now add of sequence from A1 to An, B1 to Bn, that's we call partial sum right here, guys. So you add sequence from A1 to An. Then this sum of sequence, this partial sum of Sn, partial sum of Tn, still maintain this inequality because each term of A is less or equal to each term of Bn. So we have this relationship. Sn is a partial sum of An, Bn is a partial sum of Tn is partial sum of Bk. So now this inequality just stays same. So Sn is a partial sum of sequence A, K. Tn is a partial sum of sequence Bk. So they keep this inequality. What happened? They take a limit. what is the end behavior of partial sum. So we're gonna see the graph is top is gonna be Tn, bottom gonna be Sn. That's behavior of each partial sum. If behavior of Tn is converse, let's see what happened. You're gonna take limit, or we're gonna check and the behavior each partial sum. What do you know from this graph, guys? Can you see what's going on there? What's going on here? Tn, partial sum of Tn close to the T, approach the T value, which meaning is partial sum of Sn also approach the S, guys, okay? Then which meaning is partial sum of Sn go to S. All right, they keep the then inequality. So you're gonna say partial sum of Sn also converge the sum of S value. Now, conclusion of this one, partial sum of Tn converges T value, meaning is series, infinity series of Bn is converse. See right there, which meaning is series of An also converse because partial sum of Sn go to S. That's the direct comparison test, guys, okay? Look at this one. Bn is a sequence, infinity series converse. An, infinite series An is converse. That's the direct comparison test, okay? Here is direct comparison test, okay? Here is compared to sequence. An is less than equal to Bn, which meaning is each term of sequence An is less or equal to each term of sequence Bn. Thinking about all you're gonna add all the sequence. Of course, less than equal to add all the sequence Bn. Another way say series of An always less or equal to series of Bn. So first one is this infinity series diverges, which meaning is this one is increasing. Then of course series of Bn is diverges because series of Bn is always greater than equal to series of An. Another way, this one, series of Bn is converse, then series of An also converse. So look at this inequality. That's how you understand this direct comparison. We're gonna use benchmark series, gonna be P series or geometric series. So we will have a first example in the next slides. Okay, let's see first example here. This one is infinity series. First, you have to find the benchmark series. Where you're gonna find the benchmark series? One of them, P series or geometric series. Look at the denominator, n squared 2n plus 3. So you have to find the benchmark series first. So An gonna be here. Let's find An, 1 over n squared plus 2n plus 3. So n squared is dominated term. So I gonna pick the Bn is 1 over n squared. So sum of 1 over n squared is gonna be P series. P value is 2, guys. P value is 2. That's why this P series converges. P value is 2. 2 is greater than 1. That's the converse. So we're gonna use direct comparison test. An, Bn. Which one is bigger? That's what we're gonna compare. So this one is converse. AN should be less than BN. Otherwise, we cannot prove this sequence converges. So let's check it out. Only compare denominator because numerator 1. So let's compare denominator first. Let's see. N squared plus 2n plus 3 always greater than n squared. Of course, right? You add 2n plus 3 more left side. Then we're gonna flip it. Reciprocal, then inequality gonna be changed. So 1 over n squared plus 2n plus 3 less than 1 over n squared. So we're gonna have infinity series right here, guys. Summation, this is infinity series, add all the sequence. This is add all the sequence 1 over n squared. This is a p series, p value is 2, that's the greater than 1. Right side converges, which meaning is direct comparison test say, we're gonna say left side also converges. That's the direct comparison test. Here's a very important concept, guys. You have to find the benchmark series. If you want to prove converge, this AN is less than BN. That's you're going to find the benchmark series. This is a P series converge. So benchmark series is going to be P series or geometric series. That's keep in mind, guys. Look at the next example, guys. Here is AN gonna be n minus 1. We want to find benchmark series which is similar to 1 over n minus 1. So I'm gonna pick Bn is 1 over n. Then you're gonna say summation 1 over n. That's the P series. P value is 1. Harmonic series. That's gonna be diverge. So what are you gonna prove here? AN, BN, you have proved AN is greater than BN. Otherwise, we cannot prove this series diverge. Okay? So look at this one. N is bigger than n minus 1. And you're gonna subtract 10 from the n. Of course, n is bigger. Let's reciprocal meaning is 1 over n is less than 1 over n minus 10. Now, this series, summation 1 over n, summation 1 over n minus 1, still right side is bigger. Left side is diverge. Right side also diverge. That's the direct comparison test, say. Another way you understand that, this one is increasing, go to infinity. Right side definitely have to go to infinity. That's why this series is gonna be diverge. Let's have another example here, guys. Direct comparison test. I put the test right there. So look at this one. You have AN gonna be 1 over 2 plus 3n, but looks familiar if we remove the 2, right? So I'm gonna say BN gonna be 1 over 3n. So let's check this infinity series. 1 over 3n, that's the geometric series. Ratio gonna be 1 over 3. That's converge because ratio is between negative 1 and positive 1. That's why this series is gonna converge. What do you have proven? This one is less than Bn. That's we're gonna prove this series converge, guys, okay? Let's check it out. 2 plus 3n definitely greater than 3n. Let's take reciprocal. That's meaning is 1 over 2 plus 3n less than 1 over 3n, which meaning is infinity series of each. This one is converse. this one also converges. So direct comparison test say this our series is gonna be converged. Let's have one more example about direct comparison test, guys. Look at this one, okay? 7 is problem, right, guys? So I'm gonna say an gonna be 3n over 7 plus 5n. If without the 7, let's check it out. Bn gonna be 3n over 5n. So what about this series? Right here, summation 3n over 5n, that's gonna be converged because R is 3 over 5. That's the geometric series. So we have proved an is less than bn. Then this series is gonna be converged, right? Let's check it out, guys. So let's check it out denominate because numerator exactly same. Check it out denominate. 7 plus 5n greater than 5n, of course. Then you're gonna be reciprocal. That's gonna be 1 over 7 plus 5n less than 1 over 5n. You're gonna times this 3n both sides. Inequality does not change, but still stay the inequality right there. Then you're gonna have infinity series. Then left series gonna be less than right series. So we already know this series converge because ratio is 3 over 5. That's between 1 and negative 1. So we're gonna say the series 3n over 7 plus 5n is converged. So here is the idea of a direct comparison. You're gonna compare the sequence directly, then one series converge, then smaller series gonna be converged. Smaller series diverge, bigger series gonna be diverge. That's the direct comparison test. Let's determine the convergence or divergence with this example. Okay, I have this series right there, 1 over 2n minus 1. Previous slide, we studied direct comparison. This series looks similar to geometric series. Let's see. Summation n equal 1 to infinity 1 over 2n. We know that this one is converged, so we say this is converged because geometric series. Then you're gonna say this is converged. Then we have proven support of our argument. Can you do the direct comparison? We can't, okay? I want to give another example. We cannot compare directly because 2n minus 1 is less than 2n. So this one is a series gonna be bigger than right series. So we cannot use direct comparison. Same is here. 1 over n plus 1 is similar 1 over n. This is diverse. So you're gonna guess left series diverse. But we cannot compare directly because n plus 1 is bigger. When you flip it, 1 over n plus 1 is less than 1 over n. So this one's supposed to be greater than 1 over n. Then we're going to say by the direct comparison, this one is diverse. But we cannot use direct comparison test here. So we're going to use different test. Here is another comparison test. We're gonna say limit comparison test, guys. Limit comparison test, here is a series an, series bn. We cannot directly compare an, bn. Series an, series bn directly. So what are you gonna do, guys? We're gonna test the limit. bn over an or an over bn. which ratio you're gonna take is the same output, same result. So Bn over An, and you take a limit, you just check the behavior. They have a limit L. L value is supposed to be between 0 and infinity. Our conclusion is two series is same behavior. Both are converge, both are diverge. That's the limit comparison test. When do you use it? It's very hard to prove inequality. It's very hard to check the inequality. Hard to compare two sequences. Then we're gonna use limit comparison test. For the safety, you're gonna do the limit comparison test all the time if you don't like direct comparison, guys. It works for some series when the comparison test works. So you have a hard time compare which is series bigger and smaller, then you can use limit comparison test. Let's have one example, guys. So we talk about this one. We cannot use direct comparison because, guys, look at this. An is 1 over 2n minus 1. Bn is 1 over n. This Bn is not always greater than An. Actually, An is greater Bn. So we cannot do direct comparison test. So we're going to use limit comparison test. Okay? So you already know this geometric series is going to be converged. Guys, this one is converged because ratio is 1.5. You already know. So if you limit of ratio Bn over An is converged, then we're going to say this series is converged. Let's check it out. So we're going to do limit n approach to infinity Bn over An. You can do the An over Bn, exactly same output result, guys. So we have Bn is 1 over 2n. An is 1 over 2n minus 1. Fraction of a fraction, we're going to simplify 1 over 2n over 1 over 2n minus 1. 1 over 2n times flip the denominator, 2n minus 1 over 1. That's going to be 2n times 1 is 2n. 2n minus 1 is numerator. Now, what you have to do, guys, is separate right there. Separate. 2n divided by 2n is 1. Minus 1 over 2n. As n approach to infinity, what happened to 1 over 2n? That sequence behavior going to 0 and approach to infinity, that 1 over 2n geometry sequence, ratio gonna be 1.5. The limit of that sequence gonna be 0. So we find the limit of ratio of two sequence, that's gonna be 1. So what is conclusion? By the limit comparison test to say this series is converge because this geometric series converge. Let's have another example for limit comparison test, guys. Look at this series right here, guys. Look at this series. This side An is 1 over square root 4n minus 1. What is Bn? Just drop this constant. Bn gonna be square root 4n. So do you know if this series gonna be converged diverge? So square root of 4 is 2. 1 over 2 square root of n. 1 over square root of n is p-value is 1.5. P-value is less than 1. That's gonna be diverge. So now we have proved limit of Bn over An. What is this? Then we're gonna say this series diverge because series of Bn is diverge if this limit between 0 and infinity. Okay, let's check it out. So limit and approach to infinity, Bn gonna be 1 over square root of 4n, an gonna be 1 over square root of 4n minus 1. So let's just simplify fraction over fraction. 1 over square root 4n, 1 over square root 4n minus 1, 1 over square root 4n times square root 4n minus 1. Denominator gonna be square root 4n, numerator square root 4n minus 1. Right there, guys. Now put the square root together. So you have limit and approach as n approach infinity square root of 4n minus 1. Then we learn how to evaluate this, right, guys? Limit go to inside the square root. So square root limit and approach to infinity 4n minus 1 over 4n. How can find this limit? You can use L'Hopital rule, guys, right? Derivative 4n minus is 4. Derivative 4n is 4. 4 over 4 is 1. So square root 1 is 1. Limit of this ratio gonna be 1. Both are converges, both are diverges. But we find infinity series Bn is diverges. Our conclusion is by the limit comparison test, this gonna be diverge. That's we find this series diverge. Let's have another example, limit comparison test. What is an, guys? What is an? That's gonna be square root n over n squared plus 1. What is bn? Just drop the constant term, or you're gonna take a dominating term. Bn gonna be square root n over n squared. Let's just simplify. Square root n over n squared gonna be 1 over square root n. What is the power of n? Guys, power is here is 1. This power is 1.5. 1 plus 1.5 gonna be 3 over 2, right? So this infinity series, this p series, p value gonna be 3 over 2. So you know that this series converges. Okay? Now, let's find, guys, let's find the limit of ratio. I'm gonna use this time an over bn. Exactly same thing. bn over an over bn. So what is an? An gonna be square root n square plus 1. Bn gonna be square root n square. Let's simplify this fraction of fraction. So square root n over n square plus 1, square root n over n square root n square plus 1, n square over square root n square root n cancel out. You have n square over n square plus 1, right? So we want to find the limit of this. Infinity over infinity, you can use L'Hopital rule. So derivative n square plus 1 is 2n. Derivative n square is 2n. Can you see the cancel out is n? Limit gonna be 1. So now, limit comparison test, what do you say? This series of bn is converges because p value is 3 over 2. That's greater than 1. Of course, this series is gonna be converged. What do you learn this session, guys? We learn direct comparison, limit comparison. Direct comparison you can compare term by term of sequence. Also, you want to prove Bn is diverse, you have to find An less than Bn, and series of An is diverse. You also want to prove series of An converges, then you have to find the sequence greater than An. Direct comparison, you're gonna compare directly. If you find direct comparison is hard, then you're gonna use limit comparison. You have find the ratio of An over Bn or Bn of An, this limit exists, which meaning is 0 and infinity. It can be 0. We cannot use in limit comparison test. Both series converge, both series diverge. When do you use limit comparison test? It's very hard to find inequality. Then you can use limit comparison test.